The international bestseller, A Brief History of Time, is the masterpiece of the famous theoretical physicist Stephen Hawking. In this book, he discusses the theories that make up the foundations of physics, like the law of gravity, general relativity, quantum mechanics, and the uncertainty principle. He takes the readers on a journey to the origin of the universe, starting with the Big Bang and beyond. Hawking believes that there could be a unified theory, which explains everything, from the tiny particles to the enormous galaxies. Questions involving the fate of the universe and the existence of a creator will be discussed in this book. Interesting facts will also be revealed. Some of them are that electrons are made up of even smaller particles, light is both a wave and a particle, and that time is not the same for everyone. The others are that the universe is continually expanding. The Big Bang is not really the beginning, and that a multiverse might exist. Stephen Hawking earned his PhD in Cambridge. He is now a director of the Department of Applied Mathematics and Physics in the university. When he was 21 years old, he was diagnosed with ALS, a motor neuron disease. Still, this did not stop him from making great achievements and receiving numerous awards. He uses a computer-based communication system provided to him by Intel. At 76, he is the oldest surviving patient of ALS. A Brief History of Time is only the first among his many publications. Our picture of the universe. Aristotle believed that the Earth was a sphere, and not a flat disk according to two arguments. First, he observed that in an eclipse, the Earth's shadow on the moon is not elliptical. It is always round. Second, in their travels, the Greeks noticed that the North Star changes its position. If you are in the North Pole, the star will seem to be directly above you. However, if you are somewhere near the equator, it will appear just over the horizon. Aristotle believed that the Earth is the center of the universe. Ptolemy, another astronomer, also believed so. He created a model wherein the sun, the moon, and the planets, and the stars revolve around the Earth within their own orbits. Though generally accepted, Ptolemy always knew that his theory was flawed. In 1514, Nicholas Copernicus, a parish priest, proposed a simpler model. His idea was that the sun is at the center, and the Earth, along with other planets, are orbiting around it. The heliocentric theory was only supported in 1610, when Galileo Galilei invented the telescope. He saw the several moons of Jupiter revolving around it. Simultaneously, Johannes Kepler modified Copernicus' theory. He suggested that the planets moved in ellipses and not in circles. Isaac Newton made a breakthrough much later, in 1687, with his theory of gravity. It is gravity that causes the moon to move around the Earth in an elliptical orbit. It is also the reason why planets revolve around the sun. Newton argued that the reason why stars don't fall into each other is because there is an infinite number of stars distributed over an infinite space. There is no central point to fall into. The stars always collapse in onto themselves. Before the 20th century, it was generally accepted that the universe has always been in a constant state. People found comfort in the thought that the universe is eternal and unchanging. According to Jewish, Christian, Muslim tradition, the universe started in a definite and not so distant past. Therefore, it is necessary to have the idea of creation. However, Aristotle and other Greek philosophers believed that the universe had existed and would continue to exist forever, and that it was only great disasters that bring back the human race to the start of civilization. Immanuel Kant explored the beginning of the universe in 1781. He had an assumption that time continues back forever, regardless of the universe. St. Augustine believed otherwise. For him, time is just an element of the universe, which God created. The static and unchanging universe idea was debunked by Edwin Hubble. In 1929, he observed that the galaxies are moving fast away from us wherever you look. This means that the universe is expanding. Hubble's proposition is correlated with the Big Bang theory. There was a time that the universe was infinitely small and dense, and if there are any events preceding the Big Bang, it would be irrelevant. In order to discuss the nature of the universe, one has to understand the meaning of scientific theory. A theory is a collective of observations which are based on a model with only a few basic elements. It should predict the result of further observations in an exact manner. However, it is always provisional. There may be future experiments that will contradict the theory. The goal of science is to supply a single theory that will explain the entire universe. Presently, physicists portray the universe based on two partial theories. The first is the theory of general relativity. This theory covers the force of gravity and the macro structure of the universe. The second is quantum mechanics, which on the other hand deals with the phenomena at the micro level. Unfortunately, they are contradictory to each other. They cannot both be correct. Physicists today strive to come up with a theory that incorporates both. The quantum theory of relativity is the major theme of this book. If there is a unified theory that governs the universe, it means that all our actions and eventual outcome is already determined. However, in relation to Darwin's natural selection, humanity may as well survive any new scientific discovery. What is important is the desire to know our origin and reason for existence. Space and time. Before Galileo and Newton, Aristotle's notion was widely accepted. According to him, the natural state of an object is at rest, and that it will move only if driven by an impulse. Because of the concept of pure thought, no one bothered to test his observation. It was Galileo who debunked this idea. He dropped objects down a slope and found that speed accelerates as a constant regardless of the weight. The reason why a feather falls slower than a ball is only because of air resistance. Newton deduced from Galileo's experiment that the real effect of force is to change the speed of the body and not to set it moving. Furthermore, the body will keep on moving in a straight line at a constant speed if it's not acted upon by any force. This is Newton's first law. Meanwhile, the second law postulates that an object will accelerate or speed up in proportion with its force. Also, the greater the mass means the smaller the acceleration. If applied to a car, the stronger the engine, the faster it accelerates. However, if the car is heavier, the acceleration slows down. Aside from the law of motion, Newton discovered the law of gravity, which states that the attraction between bodies is proportional to the mass of each body. It also states that the further apart the bodies, the smaller the force. This law applies to the orbits of the Earth, the Moon, and the planets. Newton postulated that there is no state of rest. If person A is sitting on a moving train, person B standing at the platform would say that person A is not at rest. Another example is a ball that bounces up and down inside the moving train. For person B, when the ball touches the floor of the moving train, for the second time, it's already 40 meters away from the first time. The non-existence of absolute rest means it could not be determined if two events happening at different times, the first and second bounce of the ball, occupied the exact same space. Therefore, there is no absolute position and there is no absolute space. Ole Christensen Romer, in 1676, first discovered that light travels at 300,000 kilometers per second. When he observed Jupiter's moons, he realized the light coming back from the moons took longer to reach us. This is because of the distance of Earth from Jupiter. James Clerk Maxwell, in 1865, made a more solid theory on light transmission. He succeeded to unify the partial theories of electricity and magnetism, thus electromagnetism. There are wave-like disturbances in an electromagnetic field. Long waves are called radio waves, the short waves infrared or microwaves, and the short ones are known as ultraviolet, gamma rays, and X-rays. Maxwell predicted that the light waves and radio waves move with defined speed. In 1905, a clerk in the Swiss Patent Office named Albert Einstein abandoned the notion of absolute time altogether. He proposed that no matter their speed, all entities follow the laws of science. Also, the speed of light should be the same for everything and everyone. Nothing may travel as fast as light. This theory was called the theory of relativity. It applies to Newton's law of motion and to Maxwell's theory as well. Its most remarkable manifestation is E equals mc squared, which represents energy, mass, and the speed of light respectively. An infinite amount of energy is required for an object to be as fast as light, because of its increasing mass. The theory of relativity put an end to the idea of absolute time. The light that we see from galaxies far, far away happened millions of years ago. What we see in the universe are events that happened in the past. The technology of GPS is based on relativity. Satellites placed on the atmosphere are adjusted so that they will correspond to the time on the surface of the Earth. This is because of the pull of Earth's gravity, which makes time run slower. If it is not done, the feeds of the GPS would be very far off and travelers would be lost. Furthermore, each individual measures time based on every location and movement. Space and time are now dynamic quantities. They affect the universe, and they are affected by the universe in turn. A person standing still cannot say that he is at rest because the Earth is spinning. This new understanding of space-time revolutionizes our view of the universe. It is expanding. It has a definite beginning, and quite possibly an end. The expanding universe. On a clear moonless night, we can see Venus, Mars, Jupiter, and Saturn shining brightly. As the Earth goes around the Sun, the planets and the stars change their position in the sky. Alpha Centauri, the nearest star from Earth, is 4 light-years away. Our Sun, meanwhile, is only 8 light-minutes away. The contemporary depiction of the universe was devised by Edwin Hubble in 1924. Hubble disclosed that our galaxy, the Milky Way, is not the only one. There are many others, and there are vast empty spaces between them. Our galaxy is 100,000 light-years across, and it is rotating slowly. Hubble also postulated that the brightness of a star depends on its luminosity and distance from Earth. He published in 1929 that the farther the galaxy, the faster it is moving away. This means that the universe is not static. It could be expanding because the distance between galaxies is growing over time. This was one of the greatest ever discoveries of the 20th century. Even Newton and Einstein did not think it possible. It was only Alexander Friedmann who set about trying to explain this expansion. He derived his assumption on 2 arguments. First, the universe looks identical wherever we look, and second, this would also be true if we were observing from anywhere else in space. Friedman's prediction was supported by Arno Penzias and Robert Wilson in 1965, when they tested a very sensitive microwave detector. They have tracked an extra noise, which could come from outer space since the frequency is the same for all directions. It may even come from beyond the solar system, because the radiation is consistent throughout the year. At the same time, Bob Dick and Jim Peebles suggested that the glow of the early universe should be visible from the Earth in the present because it should only be reaching us now. However, the expanding universe means that this light had shifted immensely, that it would only be perceived as microwave radiation. Friedman's model showed that the galaxies move away from one another. The universe can be compared to a balloon painted with spots. If the balloon is steadily blown up, the distance between the spots will grow. The more distance means faster movement. No spot can be pinpointed as the center of expansion. The farther apart the spots, the faster they will be moving. However, the question is the following: will contraction begin for the universe in the future, or will its expansion continue? Remember that to calculate the present expansion rate, you need to determine the speed at which the other galaxies are moving away. However, their distances can only be measured indirectly. This brings us to the assumption that the universe expands between 5 to 10% every billion years. Furthermore, the total mass of the stars is extremely less than the required amount to halt the expansion. We can gather from this evidence that the universe will continue to expand forever, and if it's progressing towards recollapse, it won't happen for at least around 10 billion more years. The most successful theory regarding the origin of the universe is the Big Bang. It assumes that the distance between nearby galaxies is zero. During that point in time, the curvature of space-time, as well as the universe's density, must have been infinite. Within a Big Bang, there is a singularity, which means that all laws of science would break down. Note that with this theory, it is assumed that the space-time fabric is smooth and almost flat. That is why all predictability fails at the Big Bang. Any event before the Big Bang will be nullified. They have no consequences, and they can and should be cut off the scientific model of the universe. Time therefore begins at the Big Bang. Another theory called steady state attempted to disprove the Big Bang. It claims that as galaxies move away, new ones are being formed in between. Additionally, the new galaxies were created from the matter that is being developed. However, the discovery of the microwave radiation by Penzias and Wilson invalidates it. Therefore, the steady-state theory should be abandoned. Roger Penrose proposed the existence of a black hole in 1965. He thought that a star collapsing under its own gravity may be trapped in a region. This void has a surface and volume that eventually shrinks to zero. The collapsed star will eventually form a singularity, where space-time and density becomes immeasurable. In a joint paper by Penrose and Stephen Hawking, dated 1970, they have proven that a Big Bang singularity must have really occurred. They based their study on mathematical theorems and the assumption that the theory of general relativity is correct. Later on, Hawking went to negate this. He proposed that if quantum effects are taken into account, there will be no singularity. General relativity, anyhow, is only an incomplete theory according to him. Therefore, there must be a time when the universe was so small that the small-scale quantum mechanics cannot be disregarded. Nevertheless, it could be concluded that the study of the universe established over ages has been changed only in 50 years. The uncertainty principle. Marquis de Laplace in the 1800s came to the assumption that the universe is deterministic. there is a set of laws that predicts everything. This assumption remained in science until the early 1900s. Succeeding research, however, has proven this false. Lord Rayleigh and Sir James Jeans suggested that a hot object, like a star for example, radiates energy at an infinite rate. Furthermore, Max Planck suggested that X-rays and other light waves could not be emitted at random, but only in certain packets called quanta. Each quantum had a certain amount of energy that increases with the frequency of the waves. They cannot be predicted. Determinism was completely debunked by Werner Heisenberg in 1926 with the uncertainty principle. It entails that in order to predict a particle's future velocity, its current position has to be measured accurately first. Using only short light waves, it would be pinpointed exactly. By Planck's hypothesis, at least one quantum should be used. However, this quantum will disturb the particle and change its velocity. To sum up, the more accurately the position of the particle is measured, the less accurate its speed will be, and vice versa. Therefore, it is impossible for them to be predicted. Heisenberg's uncertainty principle doesn't only apply to particles. It is fundamental and has strong repercussions on the Earth as a whole. In the 1920s, Heisenberg and Erwin Schrödinger and Paul Dirac formulated the quantum mechanics based on the uncertainty principle. In this theory, particles do not have distinct positions and velocities. Instead, they are under a quantum state, which is a combination of position and velocity. Quantum mechanics predicts a number or a set, not a single one, of possible outcomes, and their corresponding probability. All these present the inevitable element of randomness into science. Though Einstein never accepted that the universe was governed by chance, quantum mechanics is at the foundation of modern chemistry and biology. It rules the behavior of transistors and circuits essential for the production of television and computers. The only limits of quantum mechanics are the concept of gravity and the large-scale framework of the universe. The gravitational pull between negative and positive charge is what keeps the nucleus orbited by electrons. The problem with this was before quantum mechanics, the general assumption was that the electrons would soon lose energy, spiral inward, and collide with the nucleus. Niels Bohr formulated a resolution for this in 1913. He thought that maybe electrons do not orbit at any random distance from the nucleus, but instead at specific distances only. This idea could be represented very well by hydrogen, which only has one electron. However, the hydrogen model cannot apply to more complex atoms. This conflict was resolved by quantum mechanics. It presumes that an electron waves around the nucleus on its specified velocity. Thereafter, it became possible to calculate the allowed orbits in more complicated atoms through equations. Quantum mechanics predict nearly everything within the bounds of the uncertainty principle. Einstein's theory, on the other hand, does not accept uncertainty. This is the reason why the two partial theories cannot be combined. Elementary particles and the forces of nature. Aristotle believed that everything was made up of four basic elements: earth, fire, air, and water. Additionally, they are acted upon by the force of gravity, sinking of water and earth, as well as levity, rising of air and fire. He also believed that matter could be divided unceasingly. Democritus, however, believed in the existence of indivisible atoms within matter. Evidence for this came up in 1803, when John Dalton pointed out that compounds are formed by atoms grouping together inside molecules. Also, in 1905, Einstein noticed the random irregular movement of dust particles in liquid. He found out that this motion is caused by the atoms colliding against each other. He called this phenomenon the Brownian motion. It was J.J. Thomson who proved the existence of the electron through a setup similar to a TV tube. He successfully accelerated negative charge using an electric field to hit a special screen producing light. Today, this is called the cathode ray experiment. Thomson derived from his observations that electrons must be coming from within the atoms. Ernest Rutherford, in 1911, came up with the exact framework of atoms. In his model, a minuscule particle called the nucleus is at the center. Orbiting around it are negatively charged electrons and positively charged protons. In 1932, Rutherford's colleague James Chadwick discovered another particle which has no electrical charge. This particle was called the neutron. Until about 30 years ago, it was thought that protons and electrons are the indivisible particles. Nonetheless, experiments where particles are made to collide with each other at exceptionally high speeds indicated that they were made up of even smaller particles. These components are called quarks. Quarks have 6 flavors, or variations. They are top, bottom, strange, charmed, up, and down. Each flavor comes in 3 colors, namely blue, red, and green. These terms, however, are just labels, because quarks are much smaller than visible light. They don't have actual colors. A proton or electron is made up of 3 assorted quarks. Everything in the universe, including light and gravity, can be described in terms of particles. And these particles have a property called spin, which tells us what the particle looks like in different directions. Spin 0 is like a dot, which looks the same for all directions. Spin 1 can be pictured as an arrow. For a particle to look the same, it needs to be rotated 360 degrees. Spin 2, meanwhile, is like a double-headed arrow, requiring 180 degrees. Particles that don't look the same with just one revolution have spin half. They need 2 complete revolutions. All particles can be divided into 2 groups. Those with spin half, which makes up matter, and those of spin 0, 1, and 2 for forces in between matter. The matter particles obey the exclusion principle, which was discovered by Wolfgang Pauli in 1925. The principle states that 2 particles cannot acquire the same position and velocity simultaneously. It explains why particles do not collapse to a high-density state. If not for the exclusion principle, quarks would not form into distinct, well-defined protons or neutrons. Atoms would therefore not exist, and everything would wound up into a dense and uneven soup. In 1928, Paul Dirac used equations to explain why the electron has spin half and why it needs 2 full revolutions. He also predicted that the electron should have a counterpart, called a positron or an anti-electron. In 1932, he succeeded in proving their existence and was awarded a Nobel Prize. Every particle has an antiparticle, even planets and creatures. And if they meet, both entities would vanish in a big flash. Force-carrying particles can be classified into 4 categories. They are, according to the force's strength and their interaction with other particles. First is the weakest of all, which is gravitational force. Unlike the other 3, it acts in large distances and attracts at all times. Gravity cannot be repulsive or cancelled out. The second is electromagnetic force, which is much stronger than gravitational force. There are 2 kinds of electric charge, positive and negative. Opposite charges attract, while same charges repulse. The electromagnetic attraction between protons and electrons is what causes them to orbit the nucleus. The third category is the weak nuclear force. It causes radioactivity and affects all particles with spin half. The fourth is the strong nuclear force, which holds the quarks together. Physicists have succeeded to unify three forces into one single theory, called the GUT, or Grand Unified Theory. However, it is not really grand or unified because it doesn't include gravity, and is therefore not a complete theory. Furthermore, it includes parameters which are chosen, not predicted, just to fit the experiment. The basic idea of GUT is that the three forces are just different facets of a single force. The strong nuclear force weakens at high energies, weak and electromagnetic forces strengthen. Under a very high energy setting, all forces become equal in strength. In reality, though, only a machine as huge as the solar system will be powerful enough to achieve this. Existing particle accelerators can only produce comparatively small amounts of energy. Using large particle accelerators, scientists have been able to produce antimatter, or antiparticles such as antiprotons or antielectrons. In the process, particles are made to collide at very high speeds to disintegrate. The resulting antimatter is therefore unique in the whole galaxy, because if there are regions in outer space where antiparticles exist, it will collide with particles and they will annihilate each other, giving off high radiation. Thus, quarks, atoms, and matter as a whole would not be formed. Black holes. Jean Michel, in 1783, wrote about a huge and dense star with a gravitational field that prevents light from emitting. It would be trapped by the star's gravity before it gets far, forming black voids in space. Light from the star would never reach the Earth, but its gravitational attraction would still be felt. This is possible because light is both a wave and a particle, thus the wave-particle duality. It was thought that light travels infinitely fast and cannot be affected by gravity. However, this was proven otherwise by old Römer, who discovered that light has a defined speed. The term black hole came from John Wheeler in 1969. It is important to know the life of stars in order to understand the origin of black holes. A star originates when a large volume of gas, hydrogen mostly, begins to collapse on itself due to its gravity. As it contracts, the more atoms collide frequently at greater speeds, making the gas heat up. Eventually, it gets so hot that when atoms meet, they don't repel anymore. Instead, they fuse with each other and form helium. The heat ensuing from this reaction is what makes stars shine. When the pressure of the gas increases with heat, it balances with the gravitational attraction. This causes the star's contraction to stop. A star can be compared to a balloon. The air pressure inside makes the balloon expand. It is then balanced by the rubber tension, causing the balloon to be intact. The star will linger on like this, but, in the long run, it will use up hydrogen and all its other fuels. More massive stars die sooner than smaller ones. It will start to wither and cool off. It can become a white dwarf or a neutron star. In 1929, Subramanian Chandrasekhar explained that when a star uses up all its fuel, it can still support itself against its own gravity because of the Pauli exclusion principle. The electrons will have different velocities and be isolated from each other. The star will therefore expand, repulse from gravity, maintaining its constant radius. However, there is a limitation. The star must not be over the Chandrasekhar limit, which is about 1 to 2 times the mass of our Sun. Lev Davidovich Landau pointed out that there is another possible outcome for a star. It was called a neutron star. Instead of electrons repulsing from gravity, it is formed by neutrons and protons. Neutron stars, which are smaller than white dwarfs, also follow the Chandrasekhar limit. Robert Oppenheimer, in 1939, proposed that those stars exceeding the Chandrasekhar limit become black holes. As the star contracts, the gravity pull becomes stronger. Even if the star has shrunk to a certain radius, gravity continues to pull even more until everything, even light, could not escape. The boundary of a black hole is called the event horizon, which is a point of no return. If an astronaut ends up there on the event horizon, he will be stretched out like spaghetti or torn apart. This is because the gravity on his feet will be much stronger than the pull on his head. The study that Roger Penrose and Stephen Hawking made in 1965 to 1970 showed that there is a singularity within a black hole. A singularity is a region within the black hole where density and space-time are infinite. Based on general relativity, all laws of science would break down in it. There would be no time and no space. However, any observer outside the event horizon will not witness the singularity, and thus be protected from it. This phenomenon is called the weak cosmic censorship hypothesis. General relativity indicated possibilities for an astronaut trapped inside a black hole to avoid the singularity and escape through a wormhole. But for Stephen Hawking, this is unrealistic. According to him, singularities are very unstable. The mere presence of the astronaut will cause a disturbance. He would not see the singularity until it hits him and ends his time. Strong cosmic censorship hypothesis predicts that singularities would exist in the distant future, like in a gravitational collapse, or in the past, like in the Big Bang. For the astronaut trapped inside, unfortunately, the singularity would always be in his future, never in his past. The event horizon, the boundary of the black hole, acts like a one-way membrane. Objects can fall through it, but nothing can get out, even light. Because of this, it's almost impossible to detect a black hole. It would be like looking for a black cat in a coal cellar. Fortunately, John Michell pointed out that a black hole still exerts a gravitational force. Correspondingly, astronomers have observed a star orbiting an unseen companion in the system's Cygnus X1. It does a spiral motion towards its companion, and it gets very hot, emitting X-rays. They estimated that the mass of the unseen object is about 6 times the mass of the Sun. Therefore, in relation to the Chandrasekhar limit, it is neither a white star nor a neutron star, but a black hole. Black holes ain't so black. Stephen Hawking thought that light rays on the event horizon must be moving in parallels, because if they run into each other, they would instead be swallowed up. The area of the black hole remains the same, or increases over time, but never decreases. This is because any matter or radiation that will fall into it will add to its area. Another scenario is if 2 black holes collided and merged, the total area will be equal or greater than their sum. This non-decreasing behavior can be related with entropy and the second law of thermodynamics. The entropy or disorder in an isolated system would always increase. When 2 systems are joined together, the entropy of the system as a whole is greater than the sum of the individual systems. It is quite like not doing repairs in your house. If things are left to themselves, disorder will tend to increase. A smaller black hole has a stronger gravitational pull than a larger one because it is denser. So, in theory, when an astronaut crosses the event horizon of a small black hole, he will be torn to pieces at once. With a larger black hole, he will float to nothingness infinitely until the singularity swallows him. Hawking studied the hypothesis that black holes emit particles and radiation. He discovered that the particles do not actually come from the black hole, but from the empty space surrounding it. Particles and antiparticles collide with each other. Sometimes they annihilate, and sometimes their energies are converted, so one falls into the black hole and the other manages to escape, making it look like the black hole emitted it. As a consequence of this process, the black hole loses energy and decreases in mass through Hawking radiation. Due to gravitational pull, its temperature increases, which speeds up the black hole's shrinking process. And before it disappears, the black hole will emit radiation for the last time in one powerful explosion. The origin and fate of the universe. The general theory of relativity predicts that the universe began in the Big Bang, and will end either in a recollapse called the Big Crunch, or in a black hole singularity. After everything is destroyed in the singularity, including space-time, only the black hole's gravitational attraction would be left. On the other hand, based on the quantum theory, the energy of all the matter, collectively called information, would be conserved and return to the universe in the long run. In addition, the black hole would evaporate and disappear. Meanwhile, there is an assumption in the science community that when the universe was small at its early stage, it might be that the effects in the quantum level cannot be ignored because of immensely strong gravitational pull. This is why scientists continue the study of unifying general relativity and quantum theory. The widely accepted history of the universe starts at the Big Bang. It may be that at the beginning, the universe was so small and its temperature was very high. Because of this, the tendency of the particles is to move around so fast that they would be able to escape attraction toward each other. But only 1 second after the Big Bang, the temperature fell drastically. At low temperature, the protons and neutrons wouldn't have the energy to escape attraction, and they would start to form nuclear reactions. Elements like hydrogen and helium began to exist. There are few proofs for these phenomena. George Gamow predicted in 1948 that radiation from the hot and early stage of the universe would still be felt in the present, though only in the temperature of absolute zero. This was proven in 1965, as discussed earlier, when Penzias and Wilson were able to detect microwave radiation from outer space. Furthermore, the Big Bang could be the explanation for why there is so much helium in space. A few hours after the Big Bang, the production of the elements would have stopped. For the next million years, the universe continued expanding without any more events, until finally, temperature dropped to a few thousand degrees, and the electrons in the nuclei have no energy left to repel electromagnetic force. They started to form atoms. In denser regions, there is stronger gravitational attraction. This would cause them to stop expanding and undergo recollapse. Matter would then start spinning and increase speed until it can balance with gravity. Thus, galaxies are formed. As time went on, hydrogen and helium gas would break up into smaller clouds. Within these clouds, atoms collided and temperature increased, forming stars. More massive stars would have stronger gravity and higher temperature. The rapid nuclear reactions within them started to convert helium to heavier elements, like carbon or oxygen. Some regions of massive stars would collapse and become black holes, neutron stars, or supernova. Other regions would be raw material for a new generation of stars. It is said that our own sun is a third-generation star. However, a small amount of heavier elements remained. They collected together and rotated continuously to form the bodies that now orbit the sun. This is how planets, like our very own, were born. The newly formed Earth was very hot and had no atmosphere. In the course of time, it cooled and acquired atmosphere from the gas emission of rocks. There was no oxygen, and instead there were a lot of other substances, like hydrogen sulfide. Primordial forms of life that thrive in hydrogen sulfide began to form macromolecules. They reproduced and flourished in the ocean. In the process of evolution, the primitive forms developed and became more complicated. These self-reproducing organisms released oxygen, which eventually changed the atmosphere. Superior forms of life began to exist, like fish and reptiles, until finally the human race evolved. The history of the universe is in agreement with all the observational evidence that we have today. Yet it doesn't answer important questions, such as the following. Why was the early universe so hot? Or, what is the cause for the high-density regions? Why is the universe so uniform on a large scale in the present? Why didn't it recollapse? The general theory of relativity cannot answer these questions on its own. This is because of its prediction that the universe started off at the Big Bang singularity, where all laws of science breaks down. Consequently, all events in the past and all predictability of the future would be gone. Space-time, in essence, begins at the Big Bang. There are many other models of the universe which follow the established laws. One of them is the chaotic boundary conditions. It assumes that the universe has infinite space, or that there are an infinite number of universes. There are also the weak and strong anthropic principles. The weak version postulates that in a universe with infinite space and time, the development of intelligent beings will only happen in specific regions with limited space and time. The strong version predicts that there are many universes, or many regions within a single one, each one with its own set of science laws. It has been proven, however, that all these models are false and unlikely to happen. There is only one universe, and it is expanding. Instead, Stephen Hawking and a few of his colleagues formulated the no-boundary proposal. It is based on the sum-over-histories approach of Richard Feynman and Einstein's idea of curved spacetime. Sum-over-histories applied on the quantum theory means that the particles do not follow a single path in space-time. They go through every path there is. Space-time, meanwhile, curves because of the gravitational field. The combination of both arrives at the assumption that space-time is finite and does not have singularities. Thus, the universe has no boundary. It can be compared to the surface of the Earth. A ship which sails towards the sunset does not fall off or run into a singularity. The Earth has no edge. Hawking concluded that the absence of singularities or boundary of space-time overthrows the need to appeal to God or formulate a new theory to explain the universe. It is self-contained and not affected by outside influences. It cannot be created or destroyed. The universe simply just exists. An omnipotent being must have created everything and then left. The universe evolved by itself, with the set of laws governing it. God didn't intervene any further. Therefore, if the universe has no beginning or end, Hawking questioned the need for a creator. The arrow of time. It was established by the general theory of relativity that time is personal. Time is relative to the observer who measures it. There is an idea of imaginary time that is comparable to directions in space. If a person goes north, she can turn around and head south. It must then follow that if a person goes forward in time, she ought to be able to turn round and go backwards. But this doesn't happen in reality. Where does the difference between past and future come from? And why do we remember the past but not the future? The past and the future are the same for the laws of science. This is in accordance to symmetries known as C, P, and T. Symmetry C means that the laws are the same for particles and antiparticles. Symmetry P means that the laws are the same for any situation and its mirror image. Symmetry T means that if you reverse the motion of all particles and antiparticles, the system should go back to what it was before. Under the combination of the two operations C and P, the laws are unchanged. Inhabitants of another planet, who are mirror images of ours and made of antimatter, would have the same laws as we do. If C, P, and T symmetries are combined, the theory would still hold. Yet, there is a big discrepancy when symmetry T alone would be considered. If a cup of tea falls off a table and breaks into pieces on the floor, the pieces won't gather themselves back up together like in a reverse video recording. It is simply not possible because of the arrow of time. There are 3 arrows of time that distinguish between the past and the future. First is the thermodynamic arrow of time, wherein, as time passes, entropy or disorder increases. The cup of tea that fell on the floor will remain broken. Second is the psychological arrow of time. The mind is conscious of the past and not the future. For us humans, we have memories of our childhood, but we do not know what will happen to us in the next 10 or 50 years. Third is the cosmological arrow of time, in which the universe is expanding and not contracting. The first arrow of time is related to the third in that when the universe was smaller at the Big Bang, it had lower entropy. As disorder increased, stars were formed, planets were formed, and we human beings evolved. There are theories saying that the Big Bang is not actually the beginning. It is just the beginning of time for us in relation to general relativity. But what if the universe is not a closed system? What if it is just part of a multiverse? Physicists think that as the universe expands, disorder will continue to increase until it reaches equilibrium. That is, if all stars have used their energy and the black holes have all evaporated, there will be empty space. But these are all just theories. They cannot be proven to be true. Though we cannot be sure what will happen in the distant future, it is for us humans to understand more of the nature of our universe. Moreover, physicists also proposed that the universe is still in a low entropy state. Our time hasn't deviated so far from the Big Bang. Therefore, at least in our perspective, our spotted balloon will continue to inflate for millions and millions of years. Wormholes and time travel. In the last chapter, time was treated like a straight railway line. Passengers can only travel one way or the other. But what if the railway has loops and branches? Is it possible for anyone to travel into the future or the past? Time travel is a favorite subject in science fiction. Just as predictions on submarines and travel to the moon came true, could it be possible that time machines will exist? One possibility is through cosmic strings. These string-like structures are hypothetical defects in space-time scattered in the universe. They can be visualized as thin cracks in a frozen lake, or the imperfections within crystals. If two cosmic strings move past each other at almost the speed of light, they would possess high density that could affect spacetime. When a spaceship circles around them, there is the possibility that it can be transported back to its own past. Suppose there is a mission to go to the nearest star 4 light-years away, the Alpha Centauri. Since the spaceship is traveling close to the speed of light, and time on the Earth is slow because of the gravitational pull, the astronauts will arrive 8 years in the future. If their destination is somewhere farther in the universe, it might be that when they come back, all their loved ones would be long dead. So, the challenge for scientists is to have a spaceship that can travel as fast as light, which is about 300,000 kilometers per second. However, an enormous amount of energy will be needed. This is now being done in CERN with large particle accelerators. Elementary particles are being made to collide at very high speed so that they will break into even smaller particles. However, researchers could only achieve 99.99% of light speed. There is another possibility other than cosmic strings and interstellar travel. If not through the speed of light, then maybe time travel could be achieved with a space-time warp. In 1935, Nathan Rosen and Albert Einstein wrote about the existence of bridges, which they named Einstein-Rosen Bridge. This bridge connects distant points in space-time, which creates a shortcut, and which lessens travel time and distance. Today, they are popularly known as wormholes. Unfortunately, these wormholes are small and unstable. It might be that as a spaceship travels through, the wormhole will pinch off, and the ship will run into a singularity. As a solution, it has been suggested that there could be a more advanced civilization able to keep the wormhole open from the other side. To do this, they must have a source of negative energy density to yield space-time with negative curvature. This theory could be visualized as 2 funnels joined at the narrow ends. With all the predictions on time travel, one may ask why a visitor from the future has not yet arrived. They might have the technology or the knowledge to do so which does not exist in the present time. The paradox lies in the fact that the past cannot be changed. But there are 2 possible resolutions for this paradox, according to Stephen Hawking. First is the consistent histories approach. It assumes that when a time traveler goes back to the past, he or she must not commit any actions that would clash with his or her life in the present. The common example is committing the mistake of killing his or her own ancestor. Hawking stated that the time traveler therefore would not be able to practice free will in the past. He or she will merely be an observer. The second resolution is the alternative histories hypothesis. It states that time travelers enter alternative histories in the past, which is different from recorded history. Within it, they can exercise their free will, having no consequences whatsoever to their present. This hypothesis is quite similar to the sum over histories proposed by Richard Feynman in quantum mechanics. The sum over histories approach states that particles or waves don't follow a single path in space-time. Instead, they go from point A to point B through every possible way. When applied to the universe, it didn't have a single history. It must have every conceivable history, each with its own probability. So, when a time traveler goes back in time, he or she may go back to one of the many random pasts. The unification of physics. Physicists have so far formulated partial theories to explain the universe. The ultimate goal is to bring all these theories into a complete, unified theory. Einstein tried to search for it in his later years, but he failed. This is because, though the laws of electromagnetic force and gravity have been established, little was known at that time about nuclear force. Moreover, Einstein did not accept the uncertainty principle. Yet it seems that it is a basic component of the universe. Therefore, this principle must be incorporated into the theory. At the start of the century, the general idea was that everything could be described using the properties of matter, such as heat conduction and electricity. The discovery of atomic structure and uncertainty principle put an end to this assumption. In 1928, it was thought that if an equation could be found to explain protons, much like Dirac's equations to electrons, it would conclude theoretical physics. The discovery of neutrons and other nuclear forces, however, crushed this idea. These imply that we should not be overconfident. The pursuit for the ultimate theory is a tedious task. The GUT, or Grand Unified Theory, brought together the partial theories of the weak, the strong, and the electromagnetic forces. However, it requires quantities, like the relative mass of particles, to be chosen so that they would comply with the predictions. This makes GUT unsatisfactory, along with the fact that it does not include gravity. The main difficulty lies in the fact that general relativity is a classical theory. It does not incorporate the uncertainty principle like in quantum mechanics. When Stephen Hawking applied the uncertainty principle in general relativity, he yielded a fascinating hypothesis. One is that black holes are not really black, and another is that the universe is completely self-contained and without boundary. The uncertainty principle implies that empty space is not actually empty. It is filled with pairs of virtual particles and antiparticles. In 1984, a likely proposal towards unification was made through the string theory. It predicts that inside a quark there is a tiny string like filament. The vibration of this string dictates the formation of a proton, or an electron, or a neutron. Thus, at the center of the formation of the universe, the galaxies, the Earth, and us humans, is the different vibrations produced by these hypothetical strings. However, there is a problem with string theory. It seems to be consistent only if space-time has more than 4 dimensions, like 10 or even 26. And this is purely impossible. It has been proven that life as we know it can only exist in a 4-dimensional space-time. That is, 3 dimensions for space and 1 dimension for time. If humans are only 2-dimensional, we would be split in 2 whenever we digest food. There would also be problems if there are more than 3 space dimensions. Since the gravitational force between 2 bodies decreases with distance, the orbits of planets, like the Earth around the Sun, would be unstable. This would result in the Earth spiraling fast away from the Sun or forward into the Sun. On a smaller scale, the electrons would either escape from the atom or would spiral towards the nucleus. Subsequently, matter would not form. Amidst all these contradictions, can there really be a complete unified theory? Or is it just a hopeless case? Stephen Hawking proposed 3 outcomes for the search. First, there might be an intellectual leap for humans in the future, which would enable them to put together all partial theories. Second, there is no ultimate theory, but instead an infinite sequence of theories, which would make predictions more accurate. And third, everything just happens in a random and arbitrary fashion. Thus, the search is futile. With quantum mechanics, we have come to realize that not all phenomena can be predicted. there will always be a degree of uncertainty. We may attribute this to the intervention of God, but then it seems that the universal randomness leads nowhere. Besides, the second possibility proposed by Hawking is more likely. It is in agreement with all observations and evidences made so far. Whenever physicists discover a new phenomena that were not predicted by the existing theory, they had to develop a more advanced one. This means that we could not be sure if we had truly found the right theory, since they cannot be proved. If the theory was mathematically consistent and constantly yields results that agreed with the previous observations, only then could we conclude that it is the correct one. And the long and noble struggle of humanity to understand the universe will be done. Because theories always change to incorporate new observations, they are never properly simplified for ordinary people. One has to be an expert to understand everything. The developments are coming so rapidly that the lectures in school are always out of date. Those who can keep up devote their whole time to study. In the end, the majority of the population are oblivious to the new discoveries or the excitement they are inducing in the field of science. If a unified theory was discovered, it has to be simplified and interpreted gradually to the general public. Then we would understand the universe as a whole. But even if we do, it does not mean that everything is already determined. After all, there's still the uncertainty principle. Besides, there's no way that mathematical equations will be able to predict human behavior. The earliest attempts to explain the universe involved spirits who acted very unpredictably and human-like. These spirits, inhabiting in nature or the celestial bodies, must be pleased to ensure good harvest or changing of the seasons. Nevertheless, over time, the early civilizations must have noticed certain regularities. For example, the fact that the sun rises in the east and then sets in the west day by day, regardless if a sacrifice has been offered to the sun god or not. These regularities at first were only obvious to the field of astronomy. However, as the civilizations developed, and in particular for the last 300 years, more laws were noticed. These led Laplace to propose scientific determinism. However, this theory did not explain what the initial structure of the universe is, or how its laws were chosen. These gaps were then left to God. Nevertheless, once the universe was made, he left and did not intervene. God, therefore, became the answer to the topics that 19th century science could not understand. The universe may indeed be proven to be self-contained. Also, the unified theory might be constructed. If so, Hawking thinks that there will be a great impact to God as the creator. Physicists have always been more involved with the question of what is the universe rather than why does it even exist. The philosophers who should have been having this inquiry have failed to keep up with the pace of science. Hence, when the unified theory is finally realized and understood by everyone, we must all take part in finding the reason for our existence. If we succeed, it would be, as Hawking put it, the ultimate triumph of human reason, akin to knowing the mind of God. Albert Einstein. It is unknown to many that Einstein was also a political activist. He was noted to say that his life was divided between politics and equations. In the First World War, he participated in anti-war demonstrations while he was a professor in Berlin. He got sickened by the waste of human lives and became an advocate for civil disobedience. This made him an outcast to his colleagues and earned him an unpopular reputation. Einstein was also greatly involved in Zionism. Though he rejected the biblical idea of a God, he had a strong awareness of anti-Semitism. Because of this, his theories were under attack. There was even a book published entitled 100 Authors Against Einstein. When Hitler came to power in 1933, Einstein was already in America. He made the decision not to return to Germany. Fearing that German scientists would build a nuclear bomb, He proposed that the American government should have its own. Nevertheless, even before the first atomic bomb detonated, he warned of the dangers of nuclear war publicly and proposed an international control of nuclear weaponry. Because of his Zionist efforts, he was offered the presidency of Israel in 1952, but declined. He said, "Equations are more important to me, because politics is for the present, but an equation is something for eternity." Galileo Galilei. Galileo Galilei was responsible for the birth of modern science. He was also one of the first to argue that man could understand how the world works just by observing it. Galileo supported the Copernican idea that the planets orbited the sun, contrary to the teachings of the Church. Once he found evidence for this, he wrote about it in Italian and not in the usual academic Latin. The result is that Galileo became widely supported outside the universities, while provoking the anger of professors who believed in Aristotle, Earth as the center of the universe. In the midst of the ban against Copernican theory, Galileo traveled to Rome to speak to the leaders of the Church. He argued that the Bible must not be a source for scientific theories since it was allegorical. Because the Catholic Church was under the threat of Protestantism, it declared Copernicanism as false and erroneous, and commanded Galileo to stop promoting it. In 1623, when a friend of Galileo became the Pope, he tried to get the decree revoked. However, all he got was a permission to write a book discussing both Aristotelian and Copernican theories, wherein he has two conditions. The first is that he would not take sides, and that the second is that he would come to a certain conclusion. It should state that man is incapable of knowing how the world works because God is omnipotent. He moves in ways unimagined by man. The second book, entitled Dialogue Concerning the Two Chief World Systems, was published in 1632. It was immediately regarded in Europe as a literary and philosophical masterpiece. However, it became a huge controversy, and earned Galileo the wrath of the Church. He was brought before the Inquisition and was sentenced to house arrest for as long as he lived. 4 years before his death, the manuscript of his second major book was smuggled to a publisher in Holland. This work, entitled Two New Sciences, discussed Copernicus and more. It marked the genesis of modern physics. Isaac Newton. Isaac Newton was a genius and an unpleasant man. He was hot-tempered and often involved with heated disputes with his peers. Following the publication of his masterpiece, Principia Mathematica, Newton rose to fame. He became the president of the Royal Society and is the first scientist ever to become a knight. Soon afterwards, Newton had a rift with John Flamsteed, who helped him with his book by providing much-needed data. After the publication, Flamsteed refused to hand over some information that Newton demanded. Newton used his power to seize the work from Flamsteed and got it published. Flamsteed brought their case to court and won a court order which prevented the distribution of his stolen work. As revenge, Newton removed all references to Flamsteed in later editions of Principia. Newton also got into a dispute with Gottfried Leibniz over the newly discovered branch of mathematics, then called calculus. Although Newton learned about calculus first, he published it much later. Articles appeared defending both sides. It was notable, however, that those in favor of Newton were originally written by him. Leibniz made the mistake of appealing to the Royal Society, in which Newton is the president. This caused him to be charged officially of plagiarism. While involved in these disputes, Newton left Cambridge and the Academy altogether. He got involved in Parliament, where he continued his active anti-Catholic politics, which started in the university. Eventually he was appointed as the Warden of the Royal Mint, and launched a huge campaign against counterfeiting. Newton was able to send several men to the gallows. and he was finally able to direct his cruelty and deceit in a more socially acceptable way. There is an anecdote about a prominent scientist who once had a lecture on astronomy. He explained that the Earth orbits around the Sun, which in turn orbits the galaxy. When he was finished with his speech, an old lady stood up and accused him that all of it was rubbish. She said that the Earth is actually a flat plate on the back of a tortoise. The expert then asked her what the tortoise is standing on. The old lady remained unshaken and still insisted that there are turtles through and through. As inhabitants of the Earth, we must be inquisitive of what is happening around us, especially now that we already have the internet and we can access information with just one click. We must not be like the old lady. As Stephen Hawking once said, the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. We don't have to be physicists to appreciate the wonders of the universe. Traveling or owning a telescope is not even necessary. There are a lot of videos which we can watch online, showing the time-lapse of the skies. The website of NASA is also accessible, wherein we can see the spectacular images taken by the Hubble telescope. Distant galaxies, supernovas, nebulae, and more are not the only theories in a book. Their colors and their grandeur can be witnessed through the lens of the Hubble telescope. It is rather curious that Stephen Hawking included the anecdotes of Einstein, Galileo, and Newton in his book. We are now aware of the fact that they were also human, amidst all their great achievements. They had their own flaws and trials, but were able to overcome them. We may learn from their stories to be passionate in our chosen fields, and be strong enough to face the challenges along the way. A Brief History of Time is only the first of many books that Stephen Hawking has written. There may be new discoveries or updates in his succeeding books. We may think that all theories have been laid out for us by the pioneers of science. However, there are many more questions to be answered and fields to be explored. Like, for example, the unified theory of physics. Life on the Earth often gets us preoccupied with our jobs or studies. We also have various hobbies or interests. They may be social media, music, or fiction characters. But astronomy and physics can be interesting as well. Stephen Hawking is not the only expert. The likes of Sean Carroll or Neil deGrasse Tyson also publish books loaded with fascinating information about the universe. To aid us in the understanding of complicated theories, we can also watch videos online. On a peaceful night, whether we are staying in the house or taking a walk outside, we can look up at the sky and see the beauty of the moon and stars. It makes us realize how individuals like us, with all our worries and inclinations, are only one tiny speck in the whole universe. With the knowledge that outside our planet, stars die and galaxies move away, we may appreciate our existence. We are not sure if it is caused by a supreme being or just by random chance, but we still must be thankful for the life we have.